Power Series Part 2, Definition and Notation. A power series is a series of the form the sum from n equals 0 to infinity of a sub n times x minus c to the n, where c is the center. It's a horizontal shift. In the last part, we saw some power series, which I will rewrite for you here. We saw that 1 over 1 minus x equals 1 plus x squared plus x cubed forever, under certain conditions. And the condition we saw was that this was true for x between -1 and 1. Now the importance of this was that we showed that a function in closed form is exactly equal to an infinite series. That is, the series converges to the closed form under certain conditions, and if we add the series forever. We saw a couple more that we dealt with. We saw that natural log of 1 plus x was a manipulation of this. It was really 1 over 1 minus negative x integrated, which gave us x minus x squared over 2 plus x cubed over 3, etc. And then arctan was a similar manipulation. And we found that arctan was x minus x cubed over 3 plus x to the 5th over 5, etc. Now the purpose of this is how we can, if not find exact value for, say, natural log of arctan, we can at least approximate values by using the first few terms in the series, whether 3 or 4 or 10 or whatever we need to use. Now, I didn't talk about when these things converge, and I will do that in the next video. Instead here, I want to get you used to sigma notation. Not only writing it, that is, writing the series in sigma notation, but being comfortable manipulating the sigma form of a series. So recall that this first one here is a geometric series whose ratio is x. So I can write the series as n equals 0 to infinity of x to the n. If I plug in n equals 0, I get x to the 0, which is 1, then x to the first plus x squared plus x cubed, and you see that we do indeed get this series over here. Well, how about the natural log of 1 plus x? Let's start by writing our sigma notation. It's n equals. I'll come back to this. I could start at 0, I could start at 1. I'll see what I write over here before I determine where I want to start. Now, one thing to notice is that this series alternates signs. Arctan of x does as well. So when we have alternating signs, we almost always have a -1 to the n or to the n plus 1 power, depending on what you choose. I notice that the first term here is positive, so I'm going to start at n equals 0, which gives me -1 to the 0 or positive 1. And then it looks like I have x to the n over n. Now I'm going to check myself. I decided to start at n equals 0. If I plug in n equals 0, I get x to the 0 over 0, which is not my first term. So what if I modify this to n plus 1? Does this work now? Well, I get my first term is negative 1 to the 0, which is 1. X to the 0 plus 1 over 1. Check. I'll do the next term. If n equals 1, I get negative 1 to the 1, so negative. I get x to the 1 plus 1, x squared, over 1 plus 1, and it looks like I have it correct. Let's write the power series for arctan of x in our sigma form. Again, n equals something to infinity. It alternates, so I'll have negative 1 to the power. If I choose n equals 0, then this does give me a positive first term. And then notice that all my powers are odd. In math, we often write odd as 2n plus 1. And I have the same power. That is, I have the same number as the power in the denominator, so that's over 2n plus 1 as well. Check yourself, plug in the first few terms, and see that this indeed is the series for arctan of x. Now let's go back and notice all three of these series are of the form some number times x minus c to the n power. In this first one, it's 1 times x minus 0 to the n. In the next one, I'm not going to go through and rewrite it, but notice that for every x to a power, I have some number that is multiplied by, in this case, negative 1 to the n over n plus 1. So when you see this negative 1 to the n over n plus 1, or whatever it is over here, recognize that it is a constant times x minus something to a power. And we have a power series. Now let's start manipulating the power series. What if I want to find a power series for the natural log of x? How could we do this? Well, for now, I'm going to start with a known one, which is the natural log of 1 plus x, which I know to be the following: x minus x squared over 2 plus x cubed over 3, etc. And then the general term that we wrote above of negative 1 to the n, x to the n plus 1 over n plus 1. So how could I get to what I want from what I have? Well, one way to do it is to think of the natural log of x as being the natural log of 1 plus quantity x minus 1. Confirm that's a true statement for yourself. So how can I get from here to here? Well, I could do it by getting from here to here, which says for every x, I can replace it with x minus 1 in parentheses. So I could do it in my series form. Every time I see x, I'm going to replace it with x minus 1 in parentheses. But I could do the exact same thing on the general case, because the closed form version equals the series version equals the series written in sigma notation. They're all the same. So if I do something to one side, I can do the exact same thing to anything else that is equal to. And now I have the series, the power series for the natural log of x. Let's take a look at one that seems a little more difficult, perhaps, but isn't really necessarily so when you get comfortable with these series. What if we want to integrate the arctan of x and get the series for that? I'm going to leave a little space here, and remember that the arctan is x minus x cubed over 3 plus x to the 5th over 5, etc. It's x to the odd power over that odd number. That's arctan. So if I wanted to find the integral of arctan, I could simply integrate the series. Well, the sigma notation for arctan was n equals 0 to infinity, negative 1 to the n, that's the alternating parts of x to an odd power over the odd number. So what if I want to find the integral of that? Okay. I could simply do the following. So let's integrate the series over here just to check ourselves. And for the sake of simplicity, let's let our constant of integration equal 0. It doesn't have to be, but let's just say that so we don't have to worry about finding it here. If I integrate the series, I get x squared over 2 minus x to the 4th over 3 times 4 plus x to the 6th over 5 times 6 minus etc. One hint that I recommend when you're doing series, do not simplify things. That's a general rule. When you simplify things, you tend to lose patterns. Now, what if I wanted to put this back into series notation? How could I do that? Well, I could try to find my patterns, and it doesn't seem too hard to do. But what if I simply integrate my general form? So I'm going to look at it like that. Once again, I'm going to start by putting n equals. I don't know if it's going to be 0 or 1. Sometimes when you integrate or differentiate, you can change the starting value, but I'll worry about that for later. Let's just integrate this term here. Notice that I have a constant, negative 1 to the n, over 2 to the n plus 1, times x to a power. Now each term is a different constant times x to a different power, but it doesn't matter because I have a constant rule and a power rule that I'll do when I integrate. Now the constant rule says just leave it alone when you integrate. And the power rule says add 1 to the power and divide by the new power. Now I know my first term up here is positive, so we're going to check to see if this matches the series right above it. So I'll try n equals 0. And if it's not correct, I can change to n equals 1 and fix it. But let's plug in the first couple terms. If I plug in n equals 0, I get negative 1 to the 0, or 1, over 2 times 0 plus 1, times x to the 2 times 0 plus 2, over 2. I certainly get the first term. Let's see if I can get the second term by plugging n equals 1. So n equals 1, I get negative 1 to the 1, or minus. And then I get 1 over 3 times, now if I plug in n equals 1, I get x to the 4th over 4. And notice that it matches my second term, and I'm convinced that I did it correctly. Let's take a look at one more example. It's going to be an important one going forward. But let's let f of x equal the following power series. The sum from 0 to infinity of x to the n over n factorial. An example of factorial would be 4 factorial, which is 1 times 2 times 3 times 4. N factorial equals 1 times 2 times all the way out to n. And I want to find a power series for f prime of x. So I'm going to write it out and do it the long way, and then we're going to see if we can do the same thing using our sigma notation. So f of x equals x to the 0 over 0 factorial. 0 factorial is defined to be 1. Plus x to the first over 1 factorial, plus x squared over 2 factorial, plus x cubed over 3 factorial, etc. Which means that f prime of x equals 0 plus 1 plus 2x over 2 factorial, which is 1 times 2, plus 3x squared over 3 factorial, which is 1 times 2 times 3, plus 4x cubed over 4 factorial, which is 1 times 2 times 3 times 4. And look what happens when I simplify. I get that f prime of x equals 1 plus x squared over 1 times 2 plus x cubed over 1 times 2 times 3, etc. Now we'll talk about this result later on, but for now I just want to practice the notation. What if I took the derivative of my sigma notation? Could we arrive at the same thing we did when we did it longhand? Well, we're doing derivatives. Again, we have a constant rule, where the constant is 1 over n factorial. It's a different constant for every x to the n, but it's a constant. And then we have a power rule. So we get n equals something to infinity, we'll fix in just a bit, of 1 over n factorial times n times x to the n minus 1, the power rule for derivatives. But, and let me do it up top where I have a little space here, what is n over n factorial? Well, it's 1 over n minus 1 factorial. A specific example is 4 over 4 factorial equals 1 over 1 times 2 times 3. So rewriting this, I still haven't figured out what I'm starting for n. I get x to the n minus 1 over n minus 1 factorial. which looks like I should start at 1 to get the terms that I need. But that's really kind of arbitrary, so I could, if I wanted to, just start it at 0 and write it as x to the n over n factorial, which is exactly where I started.